Hello everyone, welcome back to this video. The subject is cryptography. The subject code is 21EC642. Now we are going to discuss about the module 2, classical encryption technique.
These are the vision and mission of the department. In today's class, we'll discuss about different classical encryption techniques, and those are symmetric cipher model, substitution techniques, transposition techniques. Textbooks are William Stallings. There is Cryptography and Network Security Principles and Practice to be referred for this module. Pearson Education, 6th edition. So this is today we'll discuss about this substitution techniques. The two basic building blocks of all encryption techniques are substitution and transposition. So here we will examine a sampling of like what might be called classical encryption techniques and a study of these techniques that enables us to illustrate the basic approaches to symmetric encryption that is used today and the types of cryptanalytic attacks that must be anticipated. So the two basic building blocks of all encryption techniques are substitution and transposition. Here we will examine these in the next sections, and here we discuss about a system that combines both substitution and transposition. A substitution technique is one in which the letters of plain text are replaced by other letters or by numbers or symbols. So if the plain text is viewed as a sequence of bits, then substitution involves replacing plain text bit patterns with ciphertext bit patterns. So the first one is Caesar cipher. The earliest known and the simplest use of a substitution cipher was by Julius Caesar. The Caesar cipher involves replacing each letter of the alphabet with the letter standing three places further down the alphabet. So as an example, here we can consider plain text as meet me after the yoga party, and its ciphertext is PHHW, PHTI, WHU, WKH, WRJD, STUWB. So here we can note that the alphabet is wrapped around so that the letter following Z is A, and we can define the transformation by listing all possibilities as the follows, like A is replaced with D if it is shifted 3 letters ahead. Similarly, B is shifted with E, C is shifted with F, D is shifted with G, E is shifted with H, and so on. So here we can see a block that assigns a numerical equivalent to each letter, as A starts with 0, B 1, C 2, D 3, E 4. Similarly till Z it is 0 to 25. Then the algorithm can be expressed as follows, like for each plaintext letter P, substituting the ciphertext letter C is written as exponential of 3 comma P, that can be written as P plus 3 mod 26. A shift may be of any amount, so that the general Caesar algorithm is C is equal to exponential encryption of K comma P, that is P plus K mod 26, where K takes on a value in the range 1 to 25. The decryption algorithm is simply can be written as P is equal to decryption of K comma C, that is equal to C minus K of mod 26. So if it is known that a given ciphertext is a Caesar cipher, then a brute force cryptanalysis is easily performed by simply trying all the 25 possible keys. So here this figure shows the results of applying this strategy to the example ciphertext. So the plain text leaps out as occupying the third line. And the three important characteristics of this problem enabled us to use a brute force cryptanalysis is: the First one is the encryption and decryption algorithms are known. Second one is there are only 25 keys to try. The language of the plain text is known and easily recognizable. In most networking situations, we can assume that the algorithms are known. What generally makes this brute force cryptanalysis impractical is the use of an algorithm that employs a large number of keys. So, for example, the triple DES algorithm that makes use of a 168-bit key that giving a key space of 2 power 168 or greater than 3.7 into 10 power 50 possible keys. So the third characteristic is also significant. If the language of the plain text is unknown, then plain text output may not be recognizable. Further, the input may be abbreviated or compressed in some fashion, again making recognition difficult. So here, next we'll discuss about monoalphabetic ciphers. So with only 25 possible keys, the Caesar cipher is far from secure. So a dramatic increase in the key space can be achieved by allowing an arbitrary substitution before proceeding. So we define this term permutation as a permutation of a finite set of elements. S is an ordered sequence of all the elements of S, with each element appearing exactly once. So for example, if S can be written as A, B, C as a set of elements, then there are six permutations of S like ABC, ACB, BAC, BCA, CAB, CBA. So in general, there are, we can say that n factorial permutations of a set of n elements. So because the first element can be chosen in one of n ways, the second in n minus 1 ways, so the third in n minus 2 ways, and so on. And recalling the assignment for the Caesar cipher, here, if instead the cipher line can be any permutation of the 26 possible alphabetic characters, then there are 26 factorial or greater than 4 into 10 power 26 possible keys. So this is 10 orders. So this is 10 orders of magnitude greater than the key space for DES and would seem to eliminate this brute force techniques for cryptanalysis. So such an approach is considered as a or is referred as a monoalphabetic substitution cipher. Because a single cipher alphabet because a single cipher alphabet is used per message. So there is another line of attack if the cryptanalyst knows the nature of the plain text, example like non-compressed English text, then the analyst can exploit the regularities of the language. And to see how such a cryptanalysis might proceed, it gives a partial example that is adapted from one. So the ciphertext to be solved is it is shown here. The ciphertext that is to be solved here. This is the ciphertext. So as a first step, the relative frequency of the letters can be determined and compared to a standard frequency distribution for English, such as is shown in this figure. And if the message were long enough, this technique alone might be sufficient. But because this is a relatively short message, we cannot expect an exact match. And the relative frequencies of the letters in the ciphertext are as follows. Like P is 13.33, Z is 11.67, S is 8.33, U is 8.33, O is 7.50, M is 6.67, and so on. So comparing this breakdown, it seems likely that cipher letters P and Z are the equivalents of plaintext letters E and T, but it's not certain which is which. So the letters S, U, O, M, and H are all of relatively high frequency and probably correspond to plain letters from the set E, H, I, N, O, R, S. The letters with the lowest frequencies, namely A, B, G, Y, I, J, are likely included in the set, that is B, J, K, Q, V, X, Z. So there are a number of ways to proceed at this point. So we could make some tentative assignments and start to fill in the plain text to see if it looks like a reasonable skeleton of a message. A more systematic approach is to look for other regularities. For example, certain words may be known to be in the text, or we could look for repeating sequences of a cipher letters and try to deduce their plain text equivalence. A powerful tool is to look at the frequency of two letter combinations, which is known as diagrams, and a similar table could be drawn up showing the relative frequency of diagrams. So the most common such diagram is TH. In our ciphertext, the most common diagram is ZW, which appears three times. So we make the correspondence of Z with T and W with H. Then by our earlier hypothesis, like we can equate P with E. Now notice that the sequence ZWP appears in the ciphertext, and we can translate that sequence as this is the most frequent trigram. That is, trigram is a three-letter combination and diagram is a two-letter combination. Notice the sequence ZWSZ in the first line. We do not know that these four letters form a complete word, but if they do, it's of the form TH dash T. So if so, S equates with A. So far, then we have this sequence. Okay, so here only four letters have been identified, but already we have quite a bit. Already we have like quite a bit of the message. Continued analysis of frequencies plus trial and error should easily yield a solution from this point. So the complete plaintext with the spaces added between words follows. Like it was disclosed yesterday that several informal but direct contacts have been made with political representatives of the Weight Congress in Moscow. So monoalphabetic ciphers are easy to break because they reflect the frequency of data of the original alphabet. A countermeasure is to provide multiple substitutes known as homophones. So for a single letter, for example, the letter E could be as assigned a number of different cipher symbols such as 16, 74, 35, and 21, with each homophone assigned to a letter in rotation or randomly. If the number of symbols assigned to each letter is proportional to the relative frequency of that letter, then single letter frequency information is completely obliterated. So the mathematician Carl Friedrich Gauss believed that he had devised in an unbreakable cipher using homophones. So however, even with homophones, each element of plaintext affects only one element of ciphertext and multiple letter patterns. So this diagram frequencies still survive in the ciphertext and making cryptanalysis relatively straightforward. And the two principal methods are used in substitution ciphers to lessen this extent to which the structure of the plain text survives. One approach is to encrypt multiple letters of plain text, and the other is to use multiple